And let's assume we're going to clean this to make it look like this, right? So this is an example. It's got some balls in it and so on. Now, how do we clean the balls? We clean the balls, very smart guy, very smart. We clean the balls by having this piece there, and then we can, if you come close. So the balls are there. Sometimes in the powders, they can actually, things can get stuck in here, right? And so what you do to clean it is you just put everything there. You probably screw it in if you could. This needs still an O-ring. It probably has an O-ring already. Okay. All right. You've got that going. There's a timer. You can time it as well with this. This one here. You can time it. You can see here from the top. There's all this fans because it can get heated up. What we do is we usually use it there to do it for about maybe 15 minutes on, 15 minutes off. Right. So let's just say if you say you want to mill for 60 minutes. Just 15 off, 15 on, 15 off and on, until the total of milling time becomes 60 minutes. Right, so it will take you a couple of hours or something like that, right? So you'll be able to do that. And the good thing about it, you can time it. You don't have to be here all the time. Now, the catch is the following. It may be a blessing in disguise that this one is not working at the moment. It may be better to stick to one thing. It's cooling there, and the same cooling is not happening here. It may make some changes, variations. Unless we can produce something like that and do it that way. But that's basically what we have at the moment. So we can look at this, working on that, maybe just work with one specs at the moment until we can maybe modify this and just fix this into something good. So that's one thing. So let us now stop it. This one. But I'm sure, but there is a switch here that you can switch on and off from here.
How do you take this one out?
Yeah, it closes because there's a safety thing, right? But we're not going to try out the safety thing, right? Because it's going at 1700 RPMs. So we're not going to do that. But you take that out. Of course, you don't want the powder to fall, right? And that's why you had the screws initially. It's just to make sure that the powder doesn't work. Then you take that out. Does anybody have a piece of paper or something? Let's just do it here as well. So take that out. Okay, you have a screwdriver. You have a screwdriver?
Shit. Oops.
Yeah.
All right. So that's what you end up. Sorry guys. That's what you end up getting. But look at that. Look at the amount of powder that come out. Look at that. The walls. Look at that. It's gone a little bit cleaner from inside. You can see that, right? I just left it there for a few minutes. You can see that there is a layer here. There is a layer of stuff. So what we do, so from the sides, this is what probably happened, right? You know, these things from the sides. Don't do that at home, guys. Always wear the gloves or wear the stuff in there, right? Always wear the gloves and masks. So what we do is probably roll faster than the powder. Alright? Now, how do you dispose of powders that are used powders, the stuff that you don't want to use anymore? You get a container.
I think it's clean.
Yeah. You get a container that's maybe a plastic container of some sort, and you write on it miscellaneous powders. We call them up, the hazardous materials people in the university. They will come and pick it up for us. And that's the same for solvents, anything that we use, anything like that in terms of safety. We have to be very, very careful in terms of safety. So everybody here has to be wearing gloves, wearing masks, right? We have them here. Look at that. What I'm saying is this. So we can do that thing, that business, and start putting it in there, have it go another maybe 10 minutes or something like that, and suddenly this stuff is going to become really, really clean. But again, wear the masks and stuff. The powders, when they come out, they can be irritating. I mean, I'm doing it now. I know it's a big deal, but for all my students, I'd like them to be protected as much as possible.
Excuse me.
Because nickel powder can irritate the skin. Okay, man, you don't want to get anything inside you, so you have the masks, you have the stuff when you're dealing with powders. Once they're compacted, then it's safer. Okay, because when it's compacted, then you can go and you can use this. Just taking all the precautions you can. The other thing,
Excuse me.
yeah. So somebody's gonna mill this stuff down just to make sure it's clean and everything. The other thing, how do we do that? So we need a paint can, simply a paint can, and I think probably something like this, guys. Look, although we can get another one that's more dedicated paint can, but imagine this. Imagine we have a can that looks like this, right? We place this in there and imagine the sample is like this. We have the powders here, everything is great, everything's there. It's put in there, this is removed, right? The can itself, we will fill it with argon. See this argon? So we'll open up the argon tank, and we'll do it slowly, but fill it up with argon. So argon is heavier than air, so it should always reside at the bottom. Then you take this piece, put it in there, right? Then you put a little bit of argon just in case, but don't try the powders to fly off or something. It's very low volume flow rate, and then it goes in like that. Then you close it. Then you close it with the lid. So after you put in the powders and everything, so all the powders are put under argon, and then it's sealed with an O-ring. And if you think this O-ring is too small, maybe you can get a bigger O-ring that you can put in there, and then it's not a bad idea to screw it in, just make sure it's tight, and then everything is under argon. Then you take that, it's under argon, then you do your milling operation. What will happen is that at some point you're going to need to take samples out. Like for example for Yvonne. At some point, let's just say she does this for half an hour of milling. And says, oh, that's interesting. Let's find out what we have there. And what I forgot to mention is that when you put the powders inside, one of the main variables that you have for mechanical milling is something called ball to powder weight ratio. So that means, let's just say, your sample is going to need this amount of powder. The good thing about it is that we have a 0.7 millimeter times 3 centimeters or whatever. We can find out what the volume is, what mass this thing is going to be when you have nickel and aluminum together. What is the mass? And it'd be great if we are able to produce multiple specimens from one milling vial. So we can do that calculation. We have the nickel has a density of 8.9 grams per centimeter cubed. Aluminum is 2.7 grams per centimeter cubed. Carbon nanotubes are, let's just say, 2 grams per centimeter cubed. It varies 1.9 to 2.1 or whatever. But you can get it from the cheaptubes.com. You look at the bottom and it will tell you what the true density is. Get that density and do it in the rule of mixtures calculations, and you'll be able to find out for that particular volume what would be the mass needed. Understand that your final piece that will have these dimensions will also have porosity inside it. So the weight is not going to be the maximum weight. So it's good for a conservative calculation, because whatever you're assuming is fully dense, but it's not. So the weight is going to be less than that. But still, use that weight as being a conservative value for this. Once you know that, then you know how much you can fill this. You cannot fill this to more than 50% of its volume. So the volume is occupied by the balls and it's occupied by the powder. This is where the tungsten carbide cobalt balls come in handy, because then they come in and you can then add less balls, less volume, but more mass, and get the same ball to powder ratio. That's what you start off doing. So for Yvonne, what I would suggest we do is, because you don't want to damage the carbon nanotubes, so what you do is you use maybe a 5-to-1 ball to powder ratio. Ball to powder ratio. So let's say you find that, well, I can get 5 samples worth of about maybe 50 grams or whatever it is, right? And you try to fit that in there, and that means you need about, again, 250 gram worth of balls that you put in there. And this is where the tungsten carbide come in and do it. If we need more tungsten carbide, let us go and purchase, because I think that will help us to be able to produce more powder, I think. Okay, so let's do that. Because the steel balls are, each one is about 1 gram. A 3mm ball is about 1 gram. The tungsten carbide is 2 grams, so it doubles it. So you can save a lot of stuff. So let's just say Yvonne then takes this, adds the powders inside, make sure that he has enough nickel to be able to produce this, and then suddenly says, okay, well, I've milled it for half an hour. I'd love to be able to take a sample out just to see what these things look like. It's absolutely fine. If she takes 1 gram worth of let's just say, you don't need a lot, by the way. If you take maybe, let's just say, half a gram or maybe 1 gram, whatever it is, it's for argument's sake, it's not the real number. Then you said, oh, well, I need to really take off 5 grams of the milling balls to maintain the same ball to powder weight ratio. That has to be constant. So always remember that, be aware of that, because we always write that in the paper. We did this, but also we were careful to maintain the same ball to powder weight ratio. So we removed the ball, right, or something like that. We can plan that beforehand. And anytime you open it, take samples, it's your friend, right? So you put it in there, and then you get the samples out, and so on, and then you can take it. And have also, it's not a bad idea, once you take out the sample, to put them in some sort of a plastic container or something, just trying to seal it away from the air as much as possible. Yeah, the catch is this: you have to be very, very, very careful when you come to take the powders out of the vial. Because what you're doing, yeah, you can do something like that, but what you're doing with this is that during the mechanical milling process, you are producing a lot of fresh surfaces, unoxidized surfaces. So when you suddenly take this out, and suddenly, if you're taking a sample out that is contained or like really on top of it like that, it can build up heat quite rapidly when it starts oxidizing, and it may even catch fire. That's how serious it is. So always when you open it under argon atmosphere. And let me come and show you the first time you do that, so I can show you how to take it out, and then wearing the glasses, wearing this, and so on. But usually the case is, it's once it's spread out, as you take it out, it's more spread out, and you take it out slowly, then it gets passivated rapidly. Right? That's one way to do it. Or we can also search for the literature to see what is the best and safest way to passivate the powders before we can use them. Let's do that, because there may be other techniques where maybe we can just simply introduce oxygen in the vial, right? But slowly, because if you do it quickly, it will still light up in the vial. But there are techniques and ways of means of doing that. Mechanical milling is one thing that we could do. If we cannot do it, we have a mechanical milling process. Book. The biggest book in mechanical milling. We have that in my office. So you guys could take it, search for it there. If you cannot search for it, I can email Dr. Surya, the person that's the author of the book. Okay, we work together. So I can email him. He can tell me what's the best. He's the #1 authority in mechanical milling in the whole world. Okay, so I can talk to him and he can tell me the best way of doing that. All right. So that's that. After you want to take the balls out. You want to take the powders out. I mean, the best way to do that is to use these sieves. Let's just say the balls are not going to go through these or something like that. You just make something, make sure it's very clean first. It's clean. And then you put it in, and then you can get the powder out from the vial afterwards. So maybe, like I said, it's a good way to do it to make sure that it's passivated properly first, and then if it is passivated properly, then that's another way of getting rid of the balls. If not, but right at the end, there may be a few powders here and there. You can just get rid of the balls like that, and then you have the rest of it there. In terms of contamination, it's not going to be contaminated because all of us are using the same type of material. It's all going to be nickel and carbon nanotube. End of story. So we have to make a very good job at cleaning these things very well at the start. Afterwards, it's a little bit here or there. There's no contamination. It's just nickel, right? But still, we clean it every now and then. Yeah.
How do you clean the sieves then? Or do you soap and water? Or is it
Clean what?
the sieves and everything?
Yeah. The sieves in the ultrasonic cleaner. So you can put that in the ultrasonic cleaner for some time. And with the ultrasonic cleaner, what you do is you fill it to some level with water. Then you take a beaker, right? A big beaker. You put it inside and fill the beaker with water, right? And then throw in the sieve inside the beaker. That's the best way of doing it. Then you leave it there for whatever it takes until you think it's clean, and then you do, because these things are used like for jewelry cleaners as well, jewelry cleaning. So that's one thing that we can do, and that's the mechanical milling job. The weighing of this, of course, everybody here knows how to use this. So once we put in the stuff there, everybody knows how to use this balance. So we can get that going. What else?
So if you're taking out like a sample, so you put your argon in, you milled it, take out your sample, and then you redo the argon and put it back in.
Yes, thank you so
Okay.
much, Vanessa.
And then you
So-
just keep doing the same
Yeah, once
process.
you take, because remember, because you're taking it out under argon,
Mhm.
so it's already under argon. So then after you do that, you just fix it back in again. So maybe what you do is maybe replenish the argon a little bit, just to make sure that
And
it's
then
definitely.
close the vial back up.
Yeah, close by inside, then screw it in inside if you're able to. Then take it out, it's ready to go. And the good thing about it is you make sure that you have an O-ring that definitely seals.
Okay.
Because once you screw it in, then it's going to be sealed. And that's the best thing to do. The other thing, we usually test it out, but nobody should go ahead and do like this. Can I breathe or not? Like I said, some people died like that. A person died like that some time back, because not here, of course, but somewhere in the world, somebody died because they had something filled, the container filled up with argon, and they basically looked in and they were doing something, but there was no oxygen, right? So there's no oxygen there. But the thing is, so one thing that people try to do is they light a match and they put it in there when there's no powder, of course, and then they see that it extinguishes because there's no oxygen. That's one way of knowing that, oh, this thing is already filled with argon. That's fine. Before they put in the vial, because there's no powder that's going to ignite. Because with powders could ignite or do something. So you have to be very careful. Always number one safety. Number one in this lab. So that's that one. We take the stuff out. Once we take the samples out, we put them in, like I said, some plastic bags. We have tons of plastic bags here. Everything's labeled. We take that in there, very well labeled it. Guys, in this lab, if you see anything that is not labeled, get it to our attention immediately, because this is very, very important. First of all, it's very unsafe, right? Especially if it's Coca-Cola or something like that and it's filled with oil or filled with, you know what I mean? That is the worst. And safety people come in and ask these questions, and it's dangerous, very dangerous. So we have to make sure that single thing here is labeled. I don't care if it's water. If it's water, you write it's water. So everything is absolutely clear. Because at some point, also on top of that, is you will find people coming in and trying to, and like inspectors and stuff will come in from the county, but also before that from here, to see, and if any one of these bottles, any single bottle, and see how many samples we have, bottles or samples, anything that's not labeled, $2,000. You could do the math, and then you will know then somebody's going to become very unpopular in the whole of the college, right? So we don't want to go there. That's there. We need to, like I say, adhere to all safety protocols. Look at this. Even this silly thing everything is labeled. This is titanium dioxide. Everything is labeled. Okay. So that's your mechanical milling. Once you have the samples there, then everything sort of starts at this point. What starts? A number of things start. Very important things. Is when you're taking the sample, that's why it's a good idea to have more materials than less. Because I'm interested to see two things. we're interested, once you mill these things, right at the beginning, when you just add these things together, you'll see the nanotubes are going to be agglomerated together like hay, and then the nickel powders are going to be at certain locations and stuff. That's it. You mill it for 15 minutes, 30 minutes. You may see still nanotubes sitting outside and have not really been dispersed inside the nickel yet. And when that happens, that means you've not really completed this, right? After some time, they get dispersed. And after that, there's a whole change in the particle size distributions. Suddenly the particles can grow and then at some point come down again in size. We want to monitor this change in particle size. This is very important because remember, we want to take these materials and we want to put them in with aluminum. So after we find out the right conditions to produce the right sizes of powders of nickel that have nanotubes inside them, then we'll mill to this level, take these materials, and then basically take that and start mixing it with the aluminum to get the 3-to-1 ratio of the particle size. Now we can mix it with what? With this rotator mixer. Maybe half an hour, 45 minutes. That's typically what it is. We leave it at about 70 RPM. Right? Yeah, we leave it about 70 RPM. And this turns around, then leave it for half an hour, 45 minutes, and then everything is mixed. After that, we take it and then we press it into the samples that you know, in the dyes or in whatever Max has produced in terms of the pieces. Now we have a green compact as it is. We can still snap it. It's very weak. That is the one that's then taken to the SHS, once we have the SHS, and then we can do the studies of the reaction waves and all these different things under vacuum and under all that stuff. That is the whole process of what we're doing. But in the characterization, for something like for Yvonne or again Chelsea, when they're doing the initial characterization of these things, is, and you guys are going to be doing it for the short nanotubes, right? But when we do this characterization, I said one thing is I would love to see the particle size. Another thing, we're going to look at the particles and say, well, are the nanotubes still in there? So there's been some people that report and say, well, if you aggressively mill, there's a good chance you may even destroy the nanotubes. Okay, I've heard people say that. So that's why we're using 5-to-1 bow ratio. Mild, but for a longer time. Take its time. But I'm interested in the particle size, then we'll take those and we'll deep etch them and be able to reveal the nanotubes inside the materials, with the nickel. That's one thing. You don't have to do that at this stage in your project, is less stuff. But the other thing is that I'm really interested to find out is, once you mill the materials, you get a certain particle size. But I really, really would love to know, what is the crystal size inside the powders? When you mill powders, the powders are deformed, they break, snap, and then reattach again. The holes are hitting the powders deform, snap, the cold work, snap, and then re-weld again. And that continues. That's how the nanotubes are entrapped inside when they re-weld again. And with time they become dispersed. But I want to find out, what is the grain size now of this particle? Because at some point it can become nano. That's one thing. The other thing I want to see is, when you first mix it, for example, you're milling now for whatever minutes it is, and we can do some X-ray diffraction. Geology has an X-ray diffractometer. We do some X-ray diffraction, and it will tell you, at this peak, you have the CNTs, the carbon nanotubes, usually at 26 degrees. It's there. You start milling, you see the peak suddenly coming down. Right. At some point, you may not even see it. It may not mean that they're not there. So that's why we have to look and investigate that. But from these peaks, there is certain peak height and stuff that we can take full width at half height. There is a way we can do this. We can calibrate it. But we can find out from the XRD. It takes you 20 minutes to do it. From that, you will find out the phases that exist in there, but also at the same time, what is the crystal size. We can calculate it using something called the Shearer formula. We do that. It's a very simple formula that we do, and we can find that these are the crystal size of it. It's usually accurate if the grain size is less than 100 nanometers. So if you end up with a crystal size more than 100 nanometers, and I've seen people reporting this in the literature, completely wrong. They say we use the Shearer formula and we got the size is 150, 200 That's rubbish. It's only accurate less than 100 nanometers. All right. So that's where we do this thing. Surya, Professor Surya, in the mechanical milling one, he has another book on X-ray diffraction. And I would try to get this book either through the library or something like that. It's a very, very important book, but it explains how to do the Shearer formula. It takes you through an exercise, how exactly to do it. So practically done. And that's what's really great about this guy. So it's a really good one to be able to get. So please look at that. Again, Surya, the same guy with mechanical milling, and then just get them. And you have all these photocopies, right, of his initial book. Just find another one on X-rays. That's that one there. And that's it.